Greetings. Anyway, so yeah, today I'm going to be doing a lesson on vectors, and I think vectors are very relevant in physics, especially for like mechanics and electromagnetism. So yeah. Okay, so without further ado, what are vectors? And to explain what vectors are, I first have to explain what scalars are. Scalars are basically quantities which only have a magnitude, as opposed to vectors. And vectors, what distinguishes vectors from scalars is that they have a magnitude and also they have a direction. For instance, if I had, let's just say, a car traveling at 2 meters per second this way, and another car traveling at 2 meters per second this way. One would obviously conclude that the speed of both cars is the same, and speed is consequently a scalar because it doesn't depend on direction, so the magnitude is the same either way. On the other hand, the velocities are not the same, even though the magnitudes of velocities are the same. And by the way, as I mentioned in an earlier video, speed is the magnitude of velocity. So even though the velocities aren't the same, the magnitudes of the velocities would indeed still be the same. But I digress. So back to why the velocities aren't the same. The directions are not the same. So for instance, v sub 1. So this first car would have a velocity of 2 meters per second, and it would be in the notes 2 meters per second in the I hat direction, and I hat's a unit vector. I'll get to this later in this video, as opposed to v2, which is negative 2 meters per second, also in the I hat direction. Or if you want, you could say it's 2 meters per second in the negative I hat direction. So yeah, as you can see, vectors depend on direction, scalars do not. And now let's talk more about how vectors work. So let's say, oh wait, that's the wrong pencil. This one's too thick. Anyways, okay, so let's say we have our x and y axes, and I'm just gonna keep it two-dimensional for now. It's just keeping it simple. When I get to cross products, I'll have to go 3D, but for now, 2D will suffice. Okay, so let's just say we have a vector that goes like this. And let's just call it R. And R is actually known as the position vector. So if I had something located here, its position would be given by R, or the vector pointing from the origin to that position. So yeah. And we can see that the coordinates of this point here are obviously 2, 1, and the origin is just 0, 0. So then what would R be? Well, R is actually just 2, 1 minus 0, 0. So it would be 2, 1. However, we do not use parentheses for vector notation. We use instead these nice angled brackets, and this denotes that it's a vector. And sometimes people will also use like vertical parentheses. And what I mean by this is they'll write it like this. And yeah, either way is fine. I personally prefer the second way, but I've noticed that the second way is more common like internationally, whereas the first way is more common in the US. Okay, so and another way to write this is 2i plus j. But I'll get back to what I and j mean later. So for now, these are the two main ways to write vectors. And to denote that a quantity is a vector, you can either draw an arrow above it like I did here, or you can type it in bold. But since I'm writing, I obviously can't put it in bold. Okay, so what is the magnitude? So we know that the direction is given by 2, 1. So we know that that means that the position of this point, which we'll actually just call P, is 2 up and oh wait, sorry. It's 2 to the right of the origin and 1 unit above the origin. So this is its direction. Now the magnitude would just be actually the length of this. So you can, for field lines, you can sort of think of magnitude as like the strength of the field. So in this case, obviously using the Pythagorean theorem, the magnitude, and by the way, you can write magnitude in one of two ways. You can either write it as like normal without any bold or anything, or you can write it in the vector form but with the two vertical lines on either side. But yeah, using the Pythagorean theorem, the magnitude of this vector would just be 2 squared plus 1 squared, which is obviously just rad 5. And yeah, so that is the magnitude, and this is the direction. Okay, Pog. So anyways, let us now discuss unit vectors. And unit vectors help us see only the direction. Like, let's say we don't really want to care about the magnitude, but we want to see the direction. So as a rule of thumb, unit vectors, by definition, always have a magnitude of 0. So unit vectors, the magnitude is always 0. And that's like kind of part of the definition of a unit vector. And now the formula for a unit vector is actually... So let's just say I want to use this as an example. So unit vectors are denoted by a hat. So r hat. And so as you can probably deduce, I hat and j hat are both unit vectors. And I'll get back to these later. So anyways, as I was saying, the formula for unit vector is actually just the normal vector over the magnitude. And I can obviously also write it like this. Same thing. So in this case, the magnitude is rad 5, and we know that the normal vector is 2, 1. So then the unit vector of r is just 2 over rad 5, and if I want to rationalize that, that would just be 2 rad 5 over 5, and then rad 5 over 5. And that is the unit vector. And as it actually, okay, I screwed up. So I don't know why I wrote that they have magnitude 0. Unit vectors have magnitude 1. Like, that's part of their definition. So 1 unit, and hence the name unit vector. And we can actually prove it right quite easily here. So if we take the magnitude, we just use the Pythagorean theorem. So if we square this, we just get 4 over 25 times 5, which is just 4 over 5, plus 1 over 5, and yeah, that's obviously just 1. So we can see that this formula here is correct in finding unit vectors. Okay, now let's talk about the unit direction vectors. So another way to write vectors, in addition to the angle, the bracket way, or the long parentheses way that I just showed you, is I hat, j hat, k hat notation. So basically, I hat, j hat, and k hat are the 3 main direction vectors. So three main unit direction vectors. So I hat is equal to 1, 0, 0. So it's like in the x direction. And by the way, I'm doing this in 3D, so that's why there's 3 quantities. And obviously, you can also write it as 1, 0, 0. But I prefer the first way, so I'm just going to use this. J hat is the y direction vector, 0, 1, 0. And lastly, k hat is in the z direction, it's 0, 0, 1. So, back to our, okay, let's just say we have some vector u, and this vector is equal to 2, 4, 5. And obviously it can be written like this. So then how would you write it in terms of I hat, j hat, and k hat, the unit direction vectors? Well, it's actually really simple. You just write it as 2 I hat plus 4 j hat plus 5 k hat. And you can easily just show this. by multiplying it out. And by the way, these 2, 4, and 5 are scalars. So basically, the purpose of a unit vector is to convert a scalar into a vector. For instance, as I said here, r hat is equal to r as a vector over the magnitude of r. But let's say we wanted to convert the magnitude to a vector, then we would just multiply it by the unit vector. So we had the magnitude times r hat is equal to r. So the purpose of the unit vector is to sort of act like a gateway between magnitude and scalars and vectors. So unit vector lets you convert a scalar to a vector and vice versa. So we can see it here. The 2, 4, and 5 are scalars. They don't really have a direction, but the unit vector being multiplied to them gives them direction. Anyway, so back to what I was saying. I can prove that this is equal to this. So I said that I is 1, 0. 0 plus 4 times 0, 1, 0 plus 5 times 0, 0, 1. And vectors are actually kind of similar to scalars in some of their properties. So it would just add up. So basically here we have 2. So let's look at the x first. So 2 plus 0 plus 0, which is just 2. 0 plus 1, 0 plus 4 plus 0 is just 4. And lastly, 0 plus 0 plus 5 is just 5. And we can see that this is indeed equal to u. Okay, so now let us talk about some of the properties of vectors. So vectors, how they add is actually kind of similar to scalars. Okay, first of all, vector addition, like scalar addition, is commutative. So what that means is if you have a as a vector plus b as a vector, this is equal to b plus a. So yeah, that's called the commutative property. And that's true for scalars, obviously. I mean, I shouldn't even have to say it. I mean, 2 plus 3 is equal to 3 plus 2. So yeah. Addition with vectors is also what's known as associative. So a plus b, and let me just draw the vectors, plus c is equal to a plus b plus c. So it's also associative. And obviously this is also true for scalars. And to subtract the vector, you just add by its opposite, which is also true for scalars. So for instance, a minus b is equal to a plus negative b. Okay, and finally, let's get to the good stuff. Let's talk about multiplication by scalars, which is actually kind of what I already showed with the unit vector example. Okay, so basically, sorry about that. Okay, so just like for variables, so for vectors, if we have this is actually just equal to what you would think it would equal, which is this. So vectors actually follow a lot of the properties of scalars, but you'll see that even though they seem very similar, they are in some ways very different. And let me just give an example. Okay, so let's draw another graph with the x and y axes. Actually, no, let's not use x and y because that's so old. Like, I don't know. It's much better to use the new letters. Yeah. You know, average X and Y enjoyer versus the Chad I and J enthusiast. Am I right? Yeah, okay. Okay, that was cringe. Anyways, so let's just say we have vectors A, for example, and this is 1, 1. and b, which is let's spice it up a bit. -3, 2. Okay, so let's just draw these ticks. Okay, they're not evenly spaced, but I mean, this is like, I never said I was an artist, basically. Yeah, okay, so let's just draw it out. So A is obviously from the origin to here, and you draw when okay, that was shit, but okay, yeah, you just pretend that's a good drawing. And B goes 3 this way, and it goes 2 up. And it's a vector, so there's an arrow like this. Okay, great. So then let's say we want to find A plus B. How would we do that? Well, it's actually pretty simple. So what you do is, so we know B is -3 back in the x directions, or sorry, so by -3 it's 3 to the left and 2 up. So when we add A plus B, we're really just saying 1, 1 plus -3, 2, which is just -2, 3. And we can actually show this. So it's 3 to the left, so this is at 1. So let's first look at the x. So this is at 1, we go 1 to the left, we're at 0, another to the left, -1, and finally, if we go 3 to the left, we are at negative, I'm dumb, okay, -2. And if we go 2 up, well then it's just 1, and yes, okay, so we're at -2 comma 3 if we add them up. So this is A, and this is B. And when adding them up, the vector A plus B, it actually goes from the origin to this point here. And it's called the resultant. So this is vector A, this is vector B, this long as vector here. Yeah, that's A plus B. Okay, so yeah. Now what if we wanted to do A minus B? Well, I said earlier that A minus B. Oh, yeah, and by the way, yeah, this is so the coordinates check out. So this is -2, 3. This is -2, 3. Okay, yeah, so anyways, back to what I was saying. So A minus B can be written as A plus -B. So and what is -B? Well, we said B is -3 comma 2, so -B should be 3 comma -2. So it goes 3 here and 2 down. So as you can see, it just points in the opposite direction of regular B. This is a regular B, so this B, this -B, da-da-da. So then our new vector should point here, and then it's 3 minus 1 minus 2. Hold up. Oh wait, okay, it's here. I'm done. And similarly, the resultant vector here, so we said this is -B, and this is starting to get real messy. So this is A minus B. And since we know what A plus B is, and we know one of the properties, I'm too lazy to prove it, but you can just prove it by yourself. We also know that this is equal to B plus A. So yeah, sick. And it's kind of hard to see with the graph, but if you didn't really get it, what the point I'm trying to convey is, so if, let's say we have vector U, and we have vector V, which looks like this. If I want to find U plus V, I just sort of make V a continuation of vector U, so let's say we have V here now, and we start from the origin here, and this vector here is actually known as vector U plus V. So yeah, not too bad. And if we want to find U minus V, then, well, -V would just be in the opposite direction, same magnitude. And now we just draw that here. And then this is U minus V. Okay, so I think I did a not too I did an okayish job of covering like how to add them, I guess. And yeah. And also multiplying vectors to scalars is just multiplication. So for instance, we have the scalar 2, and let's say we have the vector, I don't know, like 300 meters per second. So then you want to, so then that would be times 2, so that'll just be 600, so it's easy peasy. Okay, so now where it gets a little more tricky is multiplying vectors by vectors. And I'll start with the easier of the two. So there's basically two ways to multiply vectors with vectors. So there's the dot product and there's the cross product. The cross product is a little tricky, so we're just going to start with the dot product first. Okay, that was shit handwriting. Dot product. Okay, great. So for the dot product, another name for it is the scalar product, because the dot product between two vectors is always a scalar. Okay, so the definition of the dot product. So the dot product is denoted by a dot, as you can probably guess by the name. So it's a dot here. So A dotted with B is AB cosine theta. And so these two are magnitudes. And so yeah, since you're multiplying two magnitudes, you get a scalar. And yeah, another way to multiply it, if you don't know the angle between the two, is to actually just look at the vectors themselves. So let's say we have A is equal to A1, A2, A3, and B is equal to B1, B2, B sub 3. Well, you're just dot product is just multiplying them and adding them up. So for instance, A dot B is really just equal to A1, B1 plus A2, B2 plus A3, B3. Boom. Okay. So yeah, that is the dot product. Okay, just as an example. And also one more thing, because of how dot products work, if I want to do A dotted with itself, it would just be A squared. And we can actually show that both ways. So if we use this way, then we can see that A dotted with itself would just be A sub 1 squared plus A sub 2 squared plus A sub 3 squared. And yeah, okay. So that would be... Sorry, that was my neck cracking. Anyways, so yeah, that would be A squared. And actually, yeah, because if the vector A was squared, then each of its components would have to be squared as well. So yeah, this makes sense. Now if we use the other way, so we have A dot A, well, this is just equal to the magnitude of A times the magnitude of A times the cosine between the two vectors. But since it's the same vector, cosine is just 0. And cosine of 0 is just 1, so it's A squared. So as you can see, yeah, this is correct. Oh yeah, and we can see that this these two are the same, because this is a magnitude, and magnitude is just equal to A is equal to the square root of A sub 1 squared plus A sub 2 squared plus A sub 3 squared. If we square this, then we also square this, and so we get rid of the square root, and we're just adding them up. So yeah, easy peasy. Yeah. And because of cosine data, this also means that if two vectors are orthogonal to each other, or in other words, perpendicular, it would just be 0. So yeah, that's the dot product. And now, for the trickier of the two products, And so I think I already said it, but the dot product is also known as a scalar product because the product is always a scalar. So that's interesting. That's cool to keep in mind. Next is the cross product. Very epic. So this is obviously, since that was the scalar product, you can probably guess that this is the vector product. And yes, it's always a vector. And now if we have A again dot B, so the magnitude of this, since it's a vector, if we want it to be a scalar, we have to take a magnitude, is equal to A times B, where these are the magnitudes, obviously, times sine theta. So this is, sorry, this is cosine theta and this is sine theta. And an example of dot product would actually be work. So we know that the integral for work, the line integral, is just f dot dr, and it's a dot product. So this is f. Let's say this is f. This is dr. So yeah, work would just be these two dotted. And so the closer dr is, or the smaller the angle between the two is, the larger the work is, because it's cosine theta. So as theta gets closer to 0, it increases. So yeah, that makes sense, because if you're pushing something, just as an example, and the force is like this, but the displacement is like this, you're not going to get much work done because it's pushing upwards. But if the force is like this and displacement's like this, you're getting more work done. So yeah, that's just an application of dot product. Okay, back to cross product. So this is the magnitude. Okay, so cross product is a bit more tricky. I just memorize it using the 3x3 matrix thing. So basically, to find the cross product, so let's say A is once again A sub 1, A sub 2, A sub 3. B is once again B sub 1, B sub 2, B sub 3. Yeah, okay. Well, then A cross B is equal to, well, I haven't actually memorized it at the top of my head, because I just find it like, it's just kind of a pain to memorize. So it's a lot easier to just compute it quickly than actually memorizing it. But yeah, so to do that, you'd actually have to use the 3x3 matrix, like determinant formula. So the top row would be ijk, or I hat, j hat, k hat. The second row would be a sub 1, a sub 2, a sub 3. And finally, the third row would be b sub 1, b sub 2, b sub 3. And so you just do it like this. And if I do that, I get, okay, so I get a sub 2 b3 minus a sub 3 b2 I plus, or it would be minus, but I'm just going to take the reverse determinant, if that makes sense. So if, yeah, because it's supposed to be minus for 3x3, but I'm just going to minus it like automatically. So oh, it did have a sub 3 b sub 1 minus a sub 1 b sub 3 j plus 2 okay. Oh yeah, I almost forgot to mention. So for dot products, it doesn't matter the order you multiply them in. So what I mean is a dot b, and you can just prove it by multiplying them out. But it's pretty easy to multiply them, because a dot b is b dot a, right? But for cross products, it's a bit more tricky, because a dot b is actually negative b or sorry, cross. This is cross product. Negative b crossed with a. So yeah, this is important to know. And also a crossed with a or b crossed with b or any vector crossed with itself is 0, which makes sense because the angle between the two vectors is 0 and sine of 0 is just 0. So magnitude would be 0, so yeah. Anyways, back to what I was saying. So yeah, this is the cross product, and you can also write this as a sub 2 b minus b sub 3 minus a sub 3 b sub 2 a sub 3 b sub 1 minus a sub 1 b sub 3, and finally a sub 1 times b sub 2 minus a sub 2 times b sub 1. And yeah, as you can see, it's quite a bit to memorize. So I just personally just I'd rather, I mean, I don't know about you, like, if you're good at memory, then go for it by any means, but personally, I just think it's easier mentally to just remember this, like, matrix configuration, then you can compute it by yourself, and it shouldn't take too long. So yeah. Okay, now, so as I mentioned earlier, dot product is scalar product, cross product is a vector product. So now you're probably wondering, how do directions work for a cross product? Since it's a vector, the product should have a direction, right? And yeah, it does. So to understand how directions work, we have to introduce this principle known as the right-hand rule. And you'll see it in physics a lot for things like torque and other examples or other applications of cross product. And if you don't know what torque is, or if you forgot, torque is the cross product between the position, or not the position, sorry. R in this context is the moment arm. So the distance between the point where the force is exerted and the axis of rotation. And then it's the force and torque's vector, obviously. So yeah, this is an application. And magnetic force is another application of cross product. And here's the formula for magnetic force on a point charge. Okay, back to what I was saying. So the right-hand rule. It's kind of hard to explain since I'm on like a computer and I don't have a camera, so I can't really show it. But basically, just hold your right hand up and point your thumb, index finger, and middle finger, or if you want the rest of your fingers, so that they're all perpendicular to each other. So your thumb should be pointing up, your index finger should be pointing forward like a gun, and then your middle finger or the rest of your fingers should be pointing in the direction perpendicular to both of them. Okay, so let's go back to our example. So we have A cross with B. And this is equal, let's say it's equal to C. So C is equal to A cross B, right? So let's give these individual things names. So let's call this one vector 1, vector 2, because the order matters, as I said earlier. So for cross product, order matters. And we'll call this, I don't know, vector 3. So if you always, anytime you have a right-hand rule like this, where this is the product and these are the vectors, so your thumb always represents this. So this should be the direction of your thumb. This should be the direction of your middle finger or any finger other than your index and thumb. If you're gonna point your three fingers in the same way, and this should be the direction of your index finger. So as an example, so as I said earlier, we have torque. So this would be thumb. This would be index, and this would be my middle finger. Okay, so let's just say okay, I'm trying to think of an example. Okay, yeah, let's say we have a door. So this is our door, And let's say someone exerts some force that goes, so the door is like this, and someone exerts force that goes into the page. And so, okay, so since the vectors are pointing in 3 directions, we have to use 3D for cross products, right? So we actually have another notation I have to get to. So let's say we want to indicate, so we know that this means something is going to the left, this means it's going to the right, this means it's going up, and this means it's going down. But since it's 3D, we need to focus on also into the screen and out of the screen, right? And so there's actually a separate notation for that. So if something is going into the screen, you just use an X. So this means something's going in like through. And you can think of it as sort of analogous to the fletchings of an arrow. So if the arrow is going into the screen, this is how the fletchings look like to you. If something's going out of the screen, you just use a point. And you can think of it as like the point of the arrow coming towards you. And yeah, so back to my example. So let's say the force is going, someone's pushing the door like into the screen, and they're pushing at this area here. And this is the axis of rotation. So an R would be here. So now point your index finger in the direction of R, your middle finger into the screen. And if you want, you can just pause it for a second, just to see, just so you can see for yourself where the torque would point. And the answer is your thumb should be pointing up. So the torque should be going up. And yeah. And that is how you use the right hand rule. And there's also another right hand rule, which I'll get to like when I talk about electromagnetism. But this one is for cross products. And yeah, so I think that's pretty much it. Let me just double check my notes real quick to see if I missed anything. Okay, yeah, and just to clarify, so using the cross product, so we have, let's just draw our z-axis, our y-axis, and our x-axis. So z is k hat, y is j hat, and x is I hat. And we can actually use the right hand rule to see how these three are related. So if we put our index finger pointing this way, our middle finger pointing this way, we can see that our thumb would actually just be pointing up. So we know that I hat times j hat is k hat. And using the identities, we then know that j hat times I hat is negative k hat. And shoot, I lost my train of thought. And also we know that gosh darn it. Oh yeah, okay, and we know that I hat dot k hat is actually negative j hat, which means that k hat times I hat is j hat. And you can actually sort of draw a little diagram to sort of help memorize it. And this is positive. If it goes the other way, it should be negative. So I hat times j hat is k hat times I hat is j hat. And finally, k hat times j hat is just, actually no, k hat times j hat is negative I hat. So this only works if they're like right next to each other. Actually no, then I would have j hat times k hat is I hat. So yeah, that would work. So then j hat times k hat is I hat, which means that k hat times j hat is negative I hat. Okay, so yeah, that is how vectors work. So vectors have magnitude and direction, scalars only have a direction. And some examples of vectors are like velocity, acceleration, even position. And so examples of scalar are speed, energy, basically something that has like a magnitude but no direction. And yes, I hoped that this video was comprehensive and that it answered all your questions about vectors, or if you already learned about vectors, that it was like a good refresher on them. And yeah, and I'm just checking my note real quick just to see if I didn't miss anything. I do not think I did. Okay, there are also vector triple products actually. I did not. I don't think I covered that, but yeah, I don't think it really shows up in physics. And you can search up, but yeah, vector triple products are not really a big deal. It's basically just a dot product and a cross product, but to compute it, you just have a 3 by 3 matrix with all three of the vectors. So yeah. Okay, yes, I think that's it. Thank you for watching, and I hope that this was helpful. And yeah. Oh shoot, okay, I just went back to like the recording thing, and for a second the screen was blank, so I panicked and I thought like that I didn't even record the screen and that the whole like time I was talking I wasted my time. But fortunately 1 second later the screen showed up. So yeah. Anyways, bye.